I'm Federico, and I'm a PhD student at ETH. And today I will talk about new Scalar and Matrix Chernoff bounds from L-infinite independence. This is a joint work with my supervisor Ravi Sting and Tali. So I will start by saying what we mean by Chernoff bound, and then I will define when a probability distribution is said to be L-infinite independent and give some example. And finally, I would like to give you an example of how we can use such bounds for an application on computer science. So I record the Chernoff inequality, which is really powerful non-asymptotic bound that I think everybody know. Here we consider a collection of positive scalar random variables that are bounded by R. We denote with X the sum of these random variables, and with mu the expectation of the sum. And then we have that the probability that a random this random variable differs from its expectation more than delta mu decrease exponentially as e to the minus mu delta squared divided by some constant. Okay, and so this has a lot of application in computer science, but actually we ask, can we do something like this if we have a collection instead of scalar random variables, we have matrix random variables. So let's consider a matrices xi, but that are square random matrices. Let's say they are also symmetric, and we denote the sum with x, and then we ask if we can find an analogous of the Chernoff bound we have for scalars. And the answer is yes. By improving some earlier results from Ashley and Binja, actually Trapp proved proved an equivalent of the matrix Chernoff bounds also for matrices. We consider a collection of positive matrices that are bounded by R norm. Now we denote with X the sum of these random variables, and with mu the norm of the sum. And here we look at the probability that the norm of the distance between our random variables and its expectation is greater than delta mu. This decreases again exponentially as e to the minus mu delta squared, but here we have b in front, where b is the size of the matrix. Okay, but now for a lot of application, actually, we don't really have this nice property that our random variables are independent, and so we would like to understand if there are a class of random variables that are not independent, but still have behavior like this, a concentration like this. And in this direction, we have actually a paper from 2018 from King and Son. They consider a collection of positive random positive matrices that are not random yet, bounded by R, and then the randomness is given by this distribution. So they take a random vector in 0, 1 to the n. This is homogeneous, which means that every outcome of this random vector contains exactly k ones and then minus k zeros. And the strong Rayleigh just means that this the entries of this random vector are negatively dependent among them, and so we denote with x the sum of these random variables that are given by taking the ith entry of the vector with the product between the ith entry of the vector with the matrix. We denoted the spectral norm of the expectation with mu, and they prove this bound, which is similar to the one for independent random variables. Actually, here there is the difference is this log k here, but in the same paper, the authors also conjecture that this log k may be an artifact of the proof and should not be there. So this is where we started with our project. The idea was to actually prove that this should not be here, and also obtain some more general distribution, this k-homogeneous strong reliability, which is a really only one example.
So k-homogeneous here means only support size?
This k-homogeneous means that this random vector, and in every outcome we only have k ones. So every time, so for every outcome of our random for every x, we is actually sum of only k matrices xi. Okay. So this is what we obtain. We look at again positive matrices bounded by R, and we have a random vector. I will give you the definition of L infinity independent in the next few minutes. For now, think about D as a constant. For example, for the strongly likely distribution that considered by King and Son, this is 2. D is equal to 2. So again, we look at this sum, and here we obtain this result. So you can see that if D is actually a constant, for example, 2, then here we obtain exactly the same form of the independent bound that we have, and I mean with some constant, different constants here at the exponent. Okay, so now I would like to give to define what we mean by two-sided L infinity independent. To do this, we consider a random vector in 0, 1, sample from a distribution that we call mu. Okay, and in general, we can take the expectation of this random vector, and this is the vector in 0, 1, the integral 0, 1 to the end, and this is we call this the vector of the marginals, because if we denote with, for example, Ci the first entry, here the first entry is the probability that C1 is equal to 1. Okay. Another thing that we can do with our vector is condition on one entry on the value of one entry. So let's select an index I between 1 and n, and we fix the I entry to be, let's say, 1. And then we sample the remaining entries of this random vector condition on this element. Okay, by doing this, we can obtain other two probability distributions that we denote with mu condition on Ci equals 0 and Ci equal 1, that are the two probability distribution when the Xi is always equal to 0 or always equal to 1. Okay, and by this we also obtain other two vector that are the marginals of these two distributions. And now we want to look at how much our original distribution mu change when we know only one entry of the outcome. And so we look at the how much mu condition on CI being 1 and CI being 0 differs from one another. In particular, we can look at the difference between these two vectors. And here comes the definition of L-infinity independence. We say that the distribution is L-infinity independent is if for every index I, when I condition on CI being 1 and CI being 0, the difference between these two marginals has we take the difference between these two marginals, we obtain a vector, we look at the sum of the absolute values of this vector, and we want them to be bounded by a constant. Furthermore, we want that this distribution is closed under conditioning, and so we impose this. This happened also for the other distribution that we obtain when we condition on whatever subset of the constant of the indices being 1 and 0. But this is actually quite natural in general for the application to ask that the property of your distribution is closed under condition. Okay, now but so this is the definition, but actually we proved the consultation bound for this, and this is helpful only if we have some example, or we wish that we can apply this to some real examples. So here there are some examples that we already know that have this property.
Why do you have the term L-infinity independence for the definition that you showed in the previous slides?
Why this called like?
Why did you call it L-infinity independent?
I answer your question in a minute.
Okay.
I list 5. Okay, so these are some distribution that all the distribution that satisfy this stochastic over property for the one who knows what it means. Then there are distributions that we if the generating polynomial of this distribution has some nice properties, in particular the 0 of this polynomial are in some particular regions of complex plane, then we can prove that distribution is infinity independent. So this also takes, for example, the strongly Rayleigh distribution. And then we have a lot of recent results that prove that this is true for some distribution that comes from physical models. Okay, and the reason why we have all these examples that are extremely recent is because this L-infinity independent actually implies another property which is called spectral independence, introduced by Anari, Liu, and Scalar, and from this spectral independent property, using some theory that comes from high-dimensional spanners, we can prove that the probability distribution we can actually we obtain fax mixing for the Monte Carlo macro chain methods for sampling from those distributions. And so here is why we call it L-infinity independence, because spectral independence is defined as the bound on the maximum eigenvalue of a matrix. And if you consider instead of the maximum eigenvalue the infinity norm, then you obtain the L-infinity independence. So this was just to mention that I'm not going into the details about this part. But I just restate the main theorem, but now you should know what L-infinity independent means. And in the remaining time, I would like to show you how we can apply this, an example of how we can apply this to computer science. So in particular, we talk about random spanning trees. So the idea is we have.
Sorry, the parameter d, is it between 0 and 1, or is it big?
The parameter d is constant, is always greater than 1. So
but it's not the difference between two probability distributions?
Yes, it's the difference between
Just taking the other one now.
Yeah.
between these two vectors. So here at least we have a 1 here, because we take the absolute value of this. So here we have a 1. Then if the distribution is independent, then here we have all zeros, because conditioning on the entry I, if all the entries are independent from one another, doesn't change the marginals of the others.
I see.
So if we have an independent distribution, here we have d equal to 1. But in general, we can I mean, the bound is interesting when d is small. So for example, constant.
Right. So I should think of it as like 1 plus something small.
Yes. For example, true for the strong relative or for the stochastic covering property. So think about 2 or 3 or something.
Isn't the difference between two probability distributions always one? No, the marginals do not sum up to 1. Okay.
No,
That's
no, the marginals do not sum
Yes,
up.
that's okay. Yes.
Okay. Yeah.
You say that independence implies spectral independence,
Yes.
so it's a stronger assumption.
Yes, it's a stronger assumption.
You have to work to show that all those applications actually satisfy a stronger assumption.
No, actually, it turns out that it's a stronger assumption, but it's easier to prove for some strange reason. So actually, in all those papers, they were interested in showing a weaker assumption, but they show the strongest and the implies the weakest. Okay, so here we have a tree. We take some spanning trees like this, and the idea is, can we take a sum of few number of spanning trees and obtain something which is similar to our original graph? So in order to define what I mean to graph for two graphs being similar, I want to introduce the Laplacian matrix, which is a matrix that represents our graph. It's a number of vertices times number of vertices matrix. And so we start from our graph, we select an edge, and in the entries that correspond to the extreme of this edge, we put this point with these values +1 and -1, and then we multiply by the weight of this edge, and we obtain a little Laplacian matrix for this edge. And then in order to obtain the Laplacian of the entire graph, we just take the sum of all these matrices. So this Laplacian matrix has a lot of nice properties. For example, if we have a vector x that defines like the potential of an electrical flow, then this expression gives the energy of that flow. But if we take x to be 0 and 1, like here, then the only entries of that sum that are not 0 are the ones between the values, the part that has 0 and the R1. So we have like the cut. So actually, for example, this LG for sure encodes all the cuts of the graph, but has also some other nice properties. And so what we want is to sample the spanning trees that resemble such that the Laplacians of this sum of spanning trees is similar to the Laplacian of the graph. So if we know that if we sample the edge such that the expectation of the weight of the edges of this tree is equal to the actual edge of the tree, then at least in expectation we have the Laplacian of our sum of random spanning trees is equal to the Laplacian of the graph. But actually, how many of these spanning trees do we need to sample in order to have that these two Laplacian are really similar? And here we can apply our theorem and say that if we sample order of log n spanning trees, and we take this average of this log n random spanning trees, then we have that this expression, so for every x transpose Lx is a 1 plus minus epsilon approximation by substituting this the Laplacian of the real graph and the Laplacian obtained by the sum of only log n spanning trees. So I would like to show you how we can prove this. So in order to apply the theorem, we need a 0-1 vector with this distribution and a collection of matrices. So for the 0-1, and also I was forgetting that this is actually type. We know that this is type. So we really need at least the order of log n spanning trees. Okay, so we take a really huge vector, which is where we concatenate the indicator vector of each of these spanning trees. We sample order of log n spanning trees, and we take the concatenation of the indicator vector of this. So every entry in this vector represents an edge in a spanning tree. And we have we know that the probability distribution of this so this probability distribution is related to them with parameter 2. And then for every edge we define this matrix, which is just the small Laplacian matrix that we define for every edge, but it's just normalized in some way, so that this matrix is positive, and after the normalization is always smaller or equal than the identity, and the idea is just that an edge is smaller or equal than the entire graph. So now if we look at this sum, which is the expectation of our sum of log n spanning trees divided by log n, we obtain that this is the expectation of one spanning tree that we know that is so it's the expectation of the graph, of the Laplacian of the graph. So this is the identity, and so from here we can actually apply the theorem. And here there is the boundary that we have from the theorem, and from this we immediately obtain the results. So what is nice about I want to show this application, because here we can see that we know that these matrices AI are bounded by the identity matrix, but actually the sum of this of n times log n these matrices divided by log n is the identity. So we really need to exploit the fact that this this bound does not depend on n or on some other parameters, but only depends on the eigenvalue of the expectation. Okay, and I think this is all I want to say.